Good morning, everyone. I want to officially welcome everybody here and all our guests who are joining in. We have a wonderful set of project presentations today. 5 groups will be presenting. And just quick instructions to all the groups that you will get 20 minutes total time slot in which you have 15 minutes to show your demo and your presentation. And we'll reserve 5 minutes for question answers from everyone. All right, and excuse me. Make sure that when you start with your title slide. Tell us about your project name, and each group member introduces themselves, and that is followed by your demo video first, and then your rest of the slides. And every member should take turns to present. Mainly the portion you worked on in your project. So we want to hear from you guys there. With that, we do have guests here. If any one of them want to introduce themselves, please go ahead so the students also know.
Morning, everybody. I'm Kelly from the Career and Life Design team.
Welcome, Kelly.
Good morning, everybody. I'm Larry Filagi. I am in a transitions right now, so I'm driving. So I'm from Stellantis. I work in automotive industry, controls and robotics industry for 25 years. And I would like to thank you for inviting me for this event. Thank you.
Welcome, Larry. Welcome back.
Thank you.
Good morning, everybody. I'm Deborah Kiefer. I work at the School of Engineering and Computer Science in the Augmented Reality Center.
Welcome, Deborah. Anybody else want to introduce themselves? All right. So with that, we will start. And our first presentation, group number 6, is going to present motion detection alarm clock. So take it away, group 6.
Okay. Are you hearing Nikki?
Hear me?
You want to start?
Yeah. All right. Hello, everyone. Today we're going to present our alarm clock called Snooze site. My name is Nikki Lipski, and I'm a senior here at Oakland University.
My name is Kary, and I'm also a senior at Oakland University. So we'll be starting by showing a demo of our project.
Is this you every morning? Do you love sleep? Have you adapted to sleep through your alarm? Or even better, turn off your alarm in your sleep? Does this newfound ability cause you to be late for your favorite class at 8 a.m. in the morning? Well, we have the solution for you. We present Snooze site.
There are multiple factors as to why we picked the motion detection alarm clock to be our final project, and one of the biggest factors was that having an 8 a.m. class, we all know how hard it is to wake up on time and not press snooze through all your alarms. So the way we found to counter that is to have an alarm clock that would detect whether if you actually got up or not, and it keeps sounding the alarm until you actually got up.
Just put in the amount of minutes and seconds you would like to sleep. Then, of course, go to sleep. And the alarm clock will wake you up and make sure that you are fully vertical before it stops the alarm. Are you worried you're going to fall off asleep once the alarm stops? Well, don't you worry. If you decide to go back to sleep and you're in a horizontal position, the alarm will sound once again. Thank you for listening, and I hope this device will help you with all your future 8 a.m. courses. Thank you.
All right. So like we mentioned in the video, the inspiration for this project was firstly how difficult it is to wake up at 8 in the morning, especially when we're in college, because sometimes you'll have to pull all-nighter or get 1 to 2 hours of sleep, and then it's really hard to get up in the morning. And I got to a point where I either slept through my alarm, or I even have an Apple Watch where that vibrates in the morning, and sometimes in my sleep I would just take it off and silence it. How I did that, still have no clue, but I was hoping to make something that would assist me with that, that if I were to fall back asleep, I can't just hit snooze and call it a day. So that was the inspiration for this project. And then so our solution was to create this alarm clock. So how this alarm clock works, like as you saw in the video, if you are in a horizontal position or seen as like sleeping, no alarm will play. Well, no, I'm sorry, the alarm will sound. And then once you are vertical, it will stop playing because like, oh, you're waking up. And then if you decide to go back to sleep, which some of us do, like if you hit snooze a couple times and you go back to bed and get a few more minutes, hoping that will help. It'll be like, hey, you gotta get up. Like no more time for snoozing, time to wake up, start the day. And it'll get you up and make sure that you didn't go back to sleep and sleep through all your alarms because it won't stop. And then how does it work? So it uses media pipe as for point detections on your body to determine if you are in the horizontal or the vertical position. And then there's the camera that would watch you while you're sleeping to see if you are sleeping or you awaken. And how it works after the alarm is set. So you put in the duration that you'd like to sleep. So like I would like to get a good 8 hours of sleep that night. So you put in 8 hours. After 8 hours, the alarm will sound, and once it starts going, if you decide to go back to sleep, it'll be like, hey, you got 8 a.m., you gotta go. So that's how it works. Okay, and the key libraries we used for this project was MediaPipe. So it detects which point of our bodies, as I previously mentioned. Numpy is like more for like the counter of figuring out how long the alarm was set. Fake sound was for the alarm sound that you heard throughout the video. And then the OpenCV was capturing the video of you sleeping and it would protect those key points on you throughout the night. And then a little bit more on MediaPipe. So it's a free Google AI Edge solution. And again, it tracks all the points in your body. So if you saw in the video, it would track my eyes and nose and detects all the parts of my body. But our main focus was the shoulders and the hips so that you can see if you're horizontal or vertical.
So in terms of the code workflow, how it works is that when the program starts, it then opens the camera, which is for the live feed analysis, which then goes into the load pose estimation model, which estimates what position you're in. And once it detects that, it tells you whether you're horizontal or vertical, which then goes to either if you are or not. And then from there on, the alarm sounds. And if you do go back to sleep, like what it said, like what you guys saw in the video, it sounds the alarm again until until it detects that you're fully up. So what scenarios where this would be very useful on is in terms of elderly care. If if an elderly does decide to get up, it notifies their caregivers, which for safety, then this would also be very useful for patient monitoring to track their movement. And in terms of smart homes, it would be very useful integrating this for safety alerts as well. Some limitations and what future improvements we could have in this project is that in terms of the camera, it does require proper visibility, since if it doesn't detect you properly, it could mess that up. And in terms of the height adjustment too, that was a problem. And for future improvements, it would be useful that detecting multiple person, not just one, and sound or motion sensors for the accuracy. So a whole summary of the project is it's a combination of OpenTV and MediaPipe for the monitoring, and it detects the movement and posture if you're asleep or not. And it's a simple and effective system. Are there any questions?
All right, good job, Group 6.
Thank you.
Okay, you want to unshare your screen?
Yes.
All right. So we're gonna open up for questions. First of all, good project. And I think we will need this for my future 8 a.m. class students. So they get this in advance and they're on time and no excuse for being late.
Mhm.
All right, with that, let's open up for questions from.
So this is Larry. I do have a question. I understand that you'll have to have a cellular phone, correct? A device with a camera. Do you
Mhm.
have any type of restriction in terms of the capabilities of the phones? Memory size or type of camera required or other type of software applications that have to be part of the phone?
So for what we did, we didn't use the phone. We actually used like a camera that we usually attach to your laptop. I haven't tried it on the phone. I'm not sure what would entail. That's another future improvement that we could implement. With that, we just ran what our project was, and we used the camera. One restriction with it was we had to have good lighting. So that's, I guess, one restriction that also something that we can implement in the future. Yeah.
Okay. Yep. Yeah, the technology for the lighting, I think will be an opportunity. I'm positive that there is mobile cameras devices that can have infrared technology, so you'll be able to detect on the days and the nights. So the opportunity to use those devices is pretty good. The important is to be able to have that environment that will make it very flexible. So not necessarily all the time the camera will face where you sleep, right? So, but if you have some other, some sort of like a device have to be definitely attached, right? To be able to detect, because you're looking for the person position, right? You don't necessarily evaluate the environment or the motion of the person along the environment. You'll have to detect the person, correct?
Correct.
Okay. All right, thank you.
Good point, Larry. And again, you mentioned that this application can be used for elder care, like in nursing home, to monitor somebody has fallen down and nice thing is that for privacy, I mean, the person is not monitoring them. It's a camera, it's a system, so that can avoid any privacy issues, somebody looking constantly in a bedroom or something. So definitely lots of uses. Other questions for this group?
Sir, I would like to ask about something for this project. First of all, it is very nice. It is very awesome. But just I want to ask something. If let's say for the sleeping person, it was covered by a quilt or something, is this system can monitor the motion, or just it is focusing on the body motion, like it is an uncovered body? This is my question.
Yeah. So right now, we are focused on like what the key points, as we mentioned. So that's another future thing. With we didn't have like in more advanced cameras, like how we mentioned, like infrared or like thermal things. We didn't have the equipment or to do that at this time, but that's definitely something that could change that or help with situations like that.
Yeah,
Thank you.
because the media pipe basically has like points on your body that detects it. So like what you said, if you have a blanket over, it might not be able to detect it. And that is definitely something that we could improve on in the future if we did have more time and more resources.
Yeah,
Thank
that
you.
was a good question, yeah. And it's for very warm climates for now, until we add that feature.
Yeah. I'm dreaming of Florida and no more snow.
Okay. Can you detect other body poses with the media pipe? other than just standing and sitting? Were you able to qualify what is standing, what is lying down and sitting?
Yeah, so it can detect like different parts, like it would detect my arms and my eyes and everything. But our main focus for this project was primarily like if you're up or if you're
Hips.
sleeping.
Say your hips.
Yeah.
Yes.
Go ahead. Can you guys hear me?
Yeah.
Mhm.
Yeah, so our main focus was like the shoulders and the hips for this project. Because
Okay.
but in the future
So
we could, yeah.
how did you detect sitting versus lying down? So were you looking at the angles?
Yeah,
Between...
the
Yeah.
angles. We were mostly
Okay.
focused on the angles of the hips and the shoulders. That was our main focus.
And did you have to do any training for this AI behind MediaPipe, or it was already trained?
It was already
It's
trained.
pre-trained.
Okay, great. Any last questions for this group? All right, good project. Good job, guys.
Thank you.
Okay, we're going to move on to the next project. Group number 7 is going to present on augmented reality communication. Take it away, group 7.
Sorry, I'm trying to share my screen here because Robert's audio isn't wanting to work.
Yeah, when you share it, check the sharing sound box.
Okay, Robert, would you mind trying again? It's telling me Zoom does not have access. I'm
Oh,
not
okay.
sure.
Yeah.
I think when you hit share, you just have to check the check sound box and it should work.
Okay, there we go. All right, good morning, everyone. Our project was machine vision assisted communication. My name is Robert. I'm a senior here.
And my name's Joey Osterhoff. I'm also a senior here studying electrical engineering.
All right, and we're gonna get right into the video.
Hi everyone, this is going to be a quick demonstration on mine and Robert's machine vision project. So basically how this works is whenever you see a bounding box around an object, you'll be able to click the bounding box and then a list of prompts will pop up. These prompts are emotions that a nonverbal or autistic kid may be feeling and may have trouble expressing. So to start off, we're going to hit person. Then a list of prompts will pop up.
I don't feel well.
Reads it out loud. And then you can even type in a custom response.
I am tired.
So you can do this for anything with a box around it. So if we put this water bottle in frame here, locates it as a bottle, we click it. Then a list of prompts pop up.
Can I have some more? Can you help me open this?
And it reads them out loud.
All right. Cell phone.
Can I play on my phone?
Cool.
Can you help me read this?
Should probably use pencil.
This is test 1 of
user interface. Come on. Wait for it to appear. Be just works better for some reason. Pencil. And then prompts for pencil pops up. I need a new pencil. Can you sharpen this or custom response?
All right, so just a little bit of introduction on this project. This project aims to help nonverbal students help communicate. So essentially what we wanted to do was give people who either couldn't talk because of certain like physical limitations or cognitive limitations, that they would have that ability to still communicate. And then just expanding on that a little bit, normally what people with autism or people on the autism spectrum use to communicate, sometimes when they don't have the verbal aspect, is they'll use something called AACs, or augmentative and alternative communications. So this could be something like a tablet where they're pressing on different symbols, or like flashcards where they hold something up. Now, the issue with these devices is it requires the user to input multiple different prompts sometimes to establish a sentence. So you see in this example, the user had to click in different prompts as opposed to maybe just verbalizing one idea, right? So we wanted to expand on this idea of the AACs by having it so it would be a little bit easier to integrate, make the user interface a little bit more friendly, and then also have it modular so that when different people are using it, there's not really like this need to understand how the device works. You just pick it up and go.
So I just want to give a brief explanation on how our system works. So originally we had tried using the YOLO V5 model, and for some reason it was kind of having trouble picking up some of the smaller objects like pencils. So we did a little research and saw that V8 is actually the best model to use, and so that's what we went with. Then we had predefined prompts that was based on a recognized object. So as you saw in the video, once you click the object, the prompt box will pop up. These were hard coded into our program, so we created the different prompts. And then we had to use an approach called class remapping because we kept encountering an issue where the data set through YOLO V8, it would think the pencil is a toothbrush. So all this was is it would basically label the toothbrush as a pencil. So that way when it recognizes the pencil, it'll correctly say it's a pencil. And then we imported a couple different libraries, tkinter that was used for our UI, and then GTTS, that's Google's text-to-speech. All that did was make it so when you click on one of the prompt boxes, it'll read it out loud. And you can go on the next slide, Robert. So this is a basic look at our code and kind of the structure it follows. So basically, before you can even run the code, you have to make sure all the libraries are imported as well as YOLO V8. And then make sure that your prompts are defined and your objects are correctly mapped. Then finally, once you're ready to start the program, the video feed will pop up. And then we get to this red decision box here. This is where it's going to start basically an endless loop where it's constantly going to be looking for an object to be clicked. Once it's clicked, it's going to open up the prompt window, where as you saw in the video, you can click any of the prompts, it'll read it out loud, and it'll generate text-to-speech. Then whenever the kid or whoever is using it is done, they can click an X, and then we go back up to that red decision box where it's going to instantly start looking for another object. So we definitely encountered a couple problems while working on this. Firstly, as I already mentioned, YOLO V5 was kind of struggling to detect smaller objects. I don't know if this was because of the camera on my laptop or Robert's laptop, but it was kind of having trouble in the beginning. Then originally when we first started this, we tried using our own data set using RoboFlow. So we went on the website, created an account, found some 1,000 image data set with classroom objects, and we're just having trouble importing it into OpenCV. And given we had a little more time, I'm sure we could have figured it out, but kind of went a different route. Another issue we found, whenever I had YOLO V8 running on my computer, it'd sound like a fighter jet's about to take off and get really loud. The computer would start to overheat. So if this were to be used in a classroom setting or at home, you would need capable technology and a laptop that's capable of running this camera. And then another issue where, as you can see in that picture there, whenever you have bounding boxes overlapped, so as you can see, I'm holding the cell phone and the bottle. If you were to click either one of those, two prompt boxes will pop up. I'm not sure why I was doing this. This could be a little confusing for the kid using it or the adult. And I'm sure if we had a little more time, we could have narrowed that down and figured out why exactly he was doing that. And then lastly, lighting. So originally, we first started testing in the engineering center. It was a bright sunny morning, and maybe that's why YOLO V5 wasn't working, but it was kind of having trouble identifying some of the objects. And lighting is normally a typical issue for any machine vision application. And then some future enhancements we would make going forward. Firstly, as I already mentioned, I think it would be really cool if we could incorporate our own data sets. So basically, depending on the environment you're in, the data set would be based off which environment you're in. So let's say you're in a classroom and you have 100 different types of pencils. You could gather all that information and put that into your own data set. And it's machine learning, so it's going to get smarter the more information it gets, and it'd be very beneficial. Another enhancement we would make would be having AI generated responses to objects. So once the camera detects a certain object, these responses will actually be AI generated. That way it's not limited to whatever you hard code into your program. It's just going to be directly through an AI. Another enhancement. So I know a group on Tuesday had facial recognition in their project. We thought that'd be cool to kind of have in ours, and it would help to have personalized prompts for specific children. So if you can see in that picture there may be a kid that is a little more fidgety than others and tends to like to have a fidget spinner. What this would do would recognize their face and then give them prompts catered to them. Another example, maybe a kid needs his allergy medication and he can kind of feel it. Whenever it sees his face, that'll be one of the prompts that pop up. Then of course, having more accurate image detection would be beneficial. And then lastly, data logging and analysis. So if there's some sort of cloud we could set up to where all this information is sent to, it could kind of help adults recognize patterns in their kids. Maybe certain prompts are being used more, and they can start to identify key patterns and kind of help out their nonverbal kids in any way they can. And yeah, those are some of our feature enhancements. And that's it. Is there any questions?
Thank you, Group 7. Good project, good demo. Can you unshare your screen? Okay, I think this was a good integration of using machine learning, augmented reality, and also voice communication using Google. So a good example of that, and can be a useful application in certain scenarios. So let's open up for questions from anyone.
Professor, and guys, maybe I have something. It is not a question. It is just I want to make a compliment for this noble idea. And I think if you cooperate with the school of someone from the School of Education, I believe you can go further. It is a really noble idea. I have no question, but I have to make this compliment, I think.
Thank
Well,
you.
I agree with that comment that I think, Robert, you were mentioning that the reason to do this project was your interaction with autistic kids
Yeah.
and difficulty of communication sometimes with them. You want to
Yeah.
elaborate more on that?
Yeah, so we had I do a teaching thing over the summer, and we had a autistic child in the program, and he was able to communicate the whole week by just pointing at things. And it was in the environment we were in, it was enough that I didn't have to worry too much because he only wanted a couple things. But I saw that as an opportunity to think, well, what if you could have that motion be captured somehow? Obviously, in the future, we would want to make it so that you don't have to press the button on the computer and it maybe recognizes that the person is pointing at something, or maybe they have some kind of thing to interact with on their end with like an iPad or something like that. But giving them the video feed so that they're in control. So.
Okay.
I have a quick question. First of all, I agree. I think that's an amazing application, and I compliment you on the project. So the camera that you were using for the project it's from the laptop looking at the subject, right? Is there that's going to be that's one scenario. Can you think of it being used on their phone? So like it's almost like they're using it as a selfie wherever they go, or do they use it as their phone to look at an object and point at an object? Is that a possibility?
Right. So the way we imagine this project being used would be to have some type of environment where the camera is pointed at the student. So that way, you're not just limited to wherever the laptop is at. Obviously, things like the phone, that's something to explore. I'm not sure I think you would have to go about connecting the phone to the laptop somehow in order to run the software, but it's a very good question.
That is a good question, Deborah, that if you're already thinking of it as a useful product, that you have your smartphone and the kid is actually carrying it and pointing at something and presses it on the phone, saying that, and it talks for him or her. You mentioned that you use YOLO version 8, right? So did you have a good idea of how much compute power was needed to run that software?
I didn't specifically check, no, but I could just tell the difference from the way my laptop was sounding, and it got very hot. And from what I researched, is it's a much more complex model, and so it takes a lot more information in, but I'm not too sure on the exact computing powers.
Okay. So my experience with running YOLO, I mean, if you're running it on a GPU, like an NVIDIA GPU, they have specialized AI machine learning, cards or computers, small computers. You could run on them these models very efficiently, and they're designed for running machine learning models on it in real time. So that's one thing. The other thing, how else can you, if you're using it on a phone, for example, how would you, if the phone doesn't have that compute power, how would you think of making it happen? Running a good AI module, but it can't run on the phone, but still using a phone for this. How would you imagine doing that now?
I would probably consider using some type of cloud-based or web-based communication between that and the phone. I'm not too well versed on how that works, but you wouldn't be able to do it locally on the phone, I believe.
That's a good point. So running a cloud, so having the intensive computation being done on the cloud, and you're using phone to relay information and then get the feedback from the cloud computer to actually output the vocal commands and all that. Yeah. Any other questions for the group? Okay, so good job, guys, again. And we are gonna move on to our group number 8, who is gonna talk about look-based media player. Take it away, group 8.
So the topic of our presentation is look-based media player. I'm Kary.
I'm Zheng Zhuo.
If you close your eyes for more than 0.5 seconds, the video will pause and resume when you open your eyes. Normal blinking will not affect video playback. If you can't look at the screen in an unexpected situation, the video will pause. And here we show the situation by turning the head up, down, left, and right. We also added the function of manually controlling video playback. Click the space bar once, the video pause. Click again, the video play. The program is set to recognize only one face. If others three will not be recognized and will not affect the video playback.
In daily life, watching videos has become an essential way for many people to relax and entertain themselves. However, due to external interruptions or unexpected situations, videos often need to be paused. For instance, some people enjoy watching shows while dining, but if they encounter a friend and need to greet to them with food covered hand, it might not be convenient to pause the video. Similarly, others have the habit of watching videos before bed, but if they fall asleep due to fatigue, they may miss parts of the video, and replaying it later can result in repeating already watched segments. In such scenarios, frequent menu options not only add complexity but may also diminish the viewing experience. To address this issue, the project purpose an intelligent video control solution based on eye detection using a camera. When the camera detects the user's eyes within a specific angle range, the video will play automatically. Conversely, when the user's gaze leaves the detection range, the video will pause automatically. This approach offers a smoother and more convenient viewing experience, minimizing manual operations and reducing the impact of external interruptions. The goal of our project is to utilize a camera to detect the user's gaze direction in real time to determine whether they are looking at the screen. When the user is looking at the screen, the video will play automatically. When they look away, the video will pause automatically. Additionally, we provide manual play and pause control function to enhance the system's interactivity and flexibility. The equipment we need is a 1080p HD camera and a computer.
We plan to implement our concept through 3 modules: the image processing module, the control logic module, and the algorithm optimization module. In the image processing module, we aim to use OpenCV to achieve region localization and key points detection. In the control logic module, we will establish a linkage between the gate state and the video play pause logic. We are also providing manual control options, such as using shortcuts to play or pause videos. In the algorithm optimization module, We aim to improve the accuracy and stability of detection, avoiding false recognition of non-facial objects as face, and ensuring the accurate localization of face feature. The most critical and challenging part of this project is the localization of facial key points. Initially, we used the hair cascade classifier for face and eye delections. As shown in the image on the left, the results were not precise. It often detects my nostril instead of my eyes. Additionally, the presence of other individuals within the camera's range also triggered detection. To address this issue, we adopt MIDI-PIP's face mesh detection model, as demonstrated in the image on the right. This model has already undergone thorough testing, so we used it as it without conducting additional tests. The face mesh model can detect face and identify 4, 6, 8 key points, coordinates. It is a robust framework that eliminates errors in detecting eyes position, notably with key points densely concentrated in areas like the nose and eyes. The model ensures highly accurate recognition results.
After achieving accurate recognition of facial features such as the eyes and nose, the next step is determining whether the user is looking at the screen. To achieve this, we use key point 4, the tip of the nose, to measure its horizontal offset. If the offset exceeds a predefined threshold, it is determined that the user has turned their head, triggering the pause logic. To make the results more visually prominent, we highlight the detected nose tip with a yellow dot. This approach aligns well with real-life sceneries. When people watching a video turn their heads to grab something, the video pauses automatically, ensuring they don't miss any important moments.
We also considered the scenario where a user might fall asleep while watching a video. To address this, we calculate the vertical height of the left and right eyes to determine whether the eyes are closed. A red dot is placed at the center of the pupil for detection. When the eyes are open and the red dot is detected, the video continues to play, as shown in the left image. If the eye height falls below a specific threshold and remains closed for more than 0.5 seconds, the red dot is no longer detected, triggering the pause logic as shown in the right image. The 0.5 seconds threshold is set to account for natural blanking, ensuring that natural blanking does not affect video playback. At the same time, we have implemented real-time key point drawing, ensuring that the camera constantly detects facial conditions to make efficient judgments. I have displayed 4 real-time key point drawing results from different angles. As shown, the system can accurately determine the current face angle. Additionally, the video will adjust in real time based on the recognized facial condition, ensuring that the video is paused or placed as soon as the facial state is detected. The next key feature is the play pause logic. We set the priority for pausing as follows. The deviation of the facial key points takes precedence over the display of the eye key points. In other words, once the facial deviation is detected, the video will pause regardless of whether the eyes are detected as open or closed at the moment. When the video is paused, we preserve the last frame and display a pause symbol at the center, allow the user to clearly see the frame where the video stopped. During playback, a 0.3-second play symbol is shown to inform the user that the video has resumed. In the absence of any interruption, the video will continue play without display any symbol, ensuring an uninterrupted view and barriers for the user.
The both functionally largely satisfies the automatic video playback control, but considering that some users prefer manual operation, we have also added a manual control feature. We set it so that pressing the spacebar once will pause the video, and pressing it again will resume playback. Using the manual pause flag each time the spacebar is pressed, the volume value is toggled to achieve the desired effect.
And this project's advantage and prospects lies in its ability to enhance users' experience by reducing manual operations and improving the convenience of video watching. A combination of automatic and manual control offer flexible to meet users' needs. Additionally, the project features high precision detections, utilizing deep learning models to ensure accurate eyes detection. The potential application of the projects are vast, including scenarios such as smart TVs, educational classrooms, and in-flight entertainment system. Moreover, the project has strong future expansions protection. We can further incorporate features like gesture control, voice recognitions, and more to create a smarter, multimodal interactive system.
In summary, the gaze-controlled intelligent media player project successfully integrates computer vision and deep learning technologies to achieve smart video playback control. In this project, we implement automatically video play and pause control based on gaze detection, while also offering users the option for manual control. The system significantly reduced the impact of manual operations on the user experience, providing a smoother and more convenient interaction. Furthermore, with optimized detection algorithms, the system maintains high accuracy and low latency under various conditions, laying a solid foundation for real-world applications.
So that's all. Thank you.
Thank you, group number 8. Good job. Good project. And it looks like you don't want to miss a single second of video watching when you design this project. I think it's a great project when you are watching lectures. So if you fall asleep, the video is going to pause and you're going to not miss a single second of the lecture, right?
Yep.
There we go. All right, let's open up for questions.
Good job, group 8. I just had a quick question. I noticed on the part where you were scanning the face that you were wearing a hat and glasses. And I was wondering if you did any testing between, like, if you scanned your face in one situation, like without glasses, if it would still recognize you and behave the way you wanted it to if you were wearing glasses when you were actually watching your video.
Actually, it's a model, so we didn't test it, but we wear the hat and glasses to run this model. It's successful.
So just to clarify, you did not train the model. The model works on any face. Is that correct?
Yes.
and it's trained to detect even if you're wearing glasses and mustaches or other facial hair, it'll still detect the face and eyes.
Yeah.
Okay. Yeah. So that was actually a good question, that if you train it on a particular face, the others will not be able to control the video player then. It works on anyone. How did you suppress when you had two people? It did not detect the face of the person behind.
Actually, we set up to detect only one person.
Okay, so there's a
Which
choice
one
of
is close to the, oh, sorry, which one is close to the camera?
Okay, that makes sense. Okay. More questions for the group?
Yes, this is Larry. Do you have any, let's say, definition of the distance between a person and the camera? And usually the human being have a tendency to close the eyes. There is a certain frequency of closing the eyes. How you eliminate that temporarily close the eyes? Not to generate stop and start, for the video many times.
Actually, we didn't consider this question. Maybe we can improve our code to of these questions.
Correct. Thank you. I appreciate it. Yes, no problem. Thank you.
Yeah, I think what Larry was trying to, I think there are two questions in there, Larry. One is like, how far away can you set, how small your face can be in the video and can still be detected?
That's correct. Yes.
That's one question. So did you test it? How far away you could sit and you could still correctly detect the face and eye open and close?
Oh, actually, we haven't thought about that yet.
Okay, so that would be a good thing to test. Like, does your face has to be a certain size in the image for it to detect, or it could do a good job even when it's a little smaller. So these are like, when you are actually testing something for real application, there are many scenarios you have to test them for so that you have a good performance. And I think the other question was, is there a way to adjust that time between, eyes open, eyes closed, so that maybe if somebody is a slow blinker, he's not pausing the video every so often?
So we choose maybe some people close eyes more than 0.5 seconds, so the video is closed. And it can, and if someone is the slow blinker, and we can choose it to more than 1 second or 2 seconds.
Okay. So you have control over that.
Yes.
Okay. And I think one last question from me is, what other applications can you think of using it besides a video player control? The same thing which you implemented for this project, watching the face and monitoring the eyes and your head turning up, down, left, right. What other applications can you think you can use this for? I mean, you already have implemented this detection mechanism. Did you think of other applications?
Actually, we consider it, and we try to create an app, and we can put the code in the app and contact like TikTok or something to run it.
Besides video control, meaning some other practical application, did you guys think of any other? Because this is a very neat way to control something.
Oh, actually, we don't think.
So what I'm suggesting is that, you know, there is a possibility you could be creative and think about, hey, now that we can detect the face and eyes blinking and head turning, what other things we could do with this information and use it for other applications. But good job, guys. Any last questions for the group? All right, with that, good job, group. And we're going to move on to group number 9, second last group of the session today, and they're going to present on 3D printer error detector. Take it away.
All right, sorry about that. Can you guys hear me? So my name is Jacob Bowden, and our project was machine vision for monitoring a 3D printer to stop the printer if any errors occurred. And my partner was...
Yeah, my name is Gabriel Castaneda.
So we'll go into the demo video. Hi, my name is Jacob Bowden, and this is our machine vision project on error detection for 3D printing. We created an AI and named it Chef Boyar 3D, which is a spaghetti detecting AI that monitors in real time a 3D printer and stops the 3D printer if any error occurs. So I'm going to turn it over to Gabe here, and he's going to explain exactly what spaghetti is.
Hello, my name is Gabriel, and I helped out with the AI deep learning portion of this project. As you can see in the video, there's a whole lot of spaghetti being detected from the AI algorithm. The spaghetti is referring to the stringy mess of material that happens when there's a failure happening on the 3D printer. So when the AI detects that, it sends the G-code command M25 to the 3D printer, and that has it stop the machine.
Okay, now with some terminology out of the way and your first look at how the AI operates, I want to set the scene for the motivation for the project in the first place. This is a true story, and it was the night before the project was due. I started one additional print just to get a few things ironed out. As it was printing, I left for a few hours, and when I came back, my printer had been murdered. There was a big mess of spaghetti all over the print bed, and there was a strand of the spaghetti that wedged itself inside the cooling fan. If you take a look at the slide deck above, it shows the actual print that destroyed the printer that day, and then the additional prints in the slide deck are from our training data set. To understand exactly why this failure mode is so detrimental to 3D printers, let's take a closer look at exactly how the printer works and the print head. So the section highlighted in red is considered the hot portion of the print head, and the section highlighted in blue is considered the cold portion of the print head. When the fan stopped working, we lost cooling, and the heat from the hot section started to creep up to the cold section. If we pop off that fan and zoom in, we can see it a little more clear. And when that heat started to creep up and heat up what was supposed to be the cold section, all the plastic inside there melted. Well, then when the print head turns off, it then re-solidifies and coats all the internal mechanisms and the working gears. So set back a little bit, we tore the printer down, we luckily had some spare parts and rebuilt it. And then we got our AI working properly, as you'll see in a moment here. So this is a huge issue in the 3D printing industry, but it also has some carryover to industrial applications. As you can tell, spaghetti is definitely an unstructured and difficult to describe phenomenon. And that's where AI excels over rule-based situations. So this application mimics some industrial applications perfectly. And that's another thing that drew us so closely to this project. So now, without further ado, take a look at the working AI. Okay, for this video, we did speed it up 2x just to get to the point. But to simulate the failure mode, this is a Delta printer that's held together with ball and socket magnetic joints. So all we did was pop out one of those joints so that the motion was sporadic and its accuracy was way off. That's why you see it printing off in midair. And once it builds up enough spaghetti for the AI to detect it, you'll see a bounding box pop up showing the confidence level, and then the M25 command being sent over to the printer. The M25 is just an asynchronous pause, tells the printer to pause and move to the back so that the user can inspect the operation, and if it's fixable, fix it. If not, cancel the print before any damage occurs. Thank you and have a great day. So just a little more information on what spaghetti is and how it's beneficial to detect it during printing. So many 3D prints, I think the average time for most of my 3D prints are roughly 5 to 6 hours, but a significant amount of them take over 24 hours to complete. And I've even done a couple that have taken multiple days to complete. So obviously this is unfeasible for a human to watch the printer at all times and ensure that everything is working properly. So to have some kind of machine vision staring over the printer at all times to stop it if anything goes awry is great. Spaghetti itself is that mess you see in the bottom right-hand corner. And that is a side effect of multiple failure modes. It can be missteps for your steppers. Your steppers don't have feedback devices on them, so they don't know if they're in the position that they've commanded to. It can be a shift in the print. If the print shifts over at one point, your 3D printer starts printing in midair, and that causes your spaghetti mess. It can also be caused, for me, like I mentioned, that Delta printer, that ball and socket joints are only magnetically held together. So if I get excess material on the print and my head hits that excess material, it actually dislodges the mechanism that holds the print head on. And that causes it to kick or canter and prints spaghetti as well. So that's exactly how we simulated it, was the most common failure mode for me, and that's popping off that arm. So the machine vision obviously helps tremendously in that scenario. In terms of the project overview, the final iteration of the project resulted in an AI that monitored the side of the project and sent a G-code command to the printer to stop it. It was set either through a USB connection or a wireless connection. But I'd like to give a little story on exactly where this project started and how it evolved over time. Because we actually started with the camera up top looking down at the printer. And it was a rule-based method at that point. We were taking a look at prints just like this, and we parsed through the G-code and looked for the minimum X value and the maximum X value, as well as the minimum and maximum Y value. We then created a bounding box around the printer, and if the print had ever stopped or ever exited the bounding box, it was considered a failure. Something went awry. And that worked great for these tiny little parts. But then when I tried to grab something big like this, it covered the majority of the bed. So the bounding box surrounded the bed, and pretty much anything was considered a good print. That seemed like a really easy issue to solve. You just, instead of looking for the minimum and maximum values, you just look at each individual line of the G-code, create an individual bounding box, and follow that. The problem with that was we really weren't looking at the problem that we were trying to solve. Because really the problem statement was to detect any type of failure. And if something happened to the print and not the print head, such as a large print like this warping and popping off the bed, which happens with more advanced materials, and that shifts over, that can cause spaghetti and be an error, and our bounding box scenario would not solve that at all. As well as it didn't have great future applications because there's additional errors like clogged nozzles, or small missteps that can cause this error as well that you wouldn't detect by being up top.
So we pivoted a little bit, literally, and brought the camera down to the side to look at the side of the print. And we started to monitor it with AI. The reason we chose AI was because the spaghetti could be different every single time and never the same. So it was really difficult to apply a rule-based method to that. And then Gabe can talk about the hardware setup.
Yeah, so we used a Raspberry Pi 5. We found it was the simplest way to incorporate YOLO v3 into the setup. We use a standard Logitech camera through USB to connect to the Raspberry Pi, and that would send all of the data over to the 3D printer. As the communication's actually done, it can be done through UARTs or wireless through the 3D printer. Can you move to the next slide? Yeah, so for the actual AI training, we trained it on a RoboFlow dataset as well as custom dataset. We have our labels all done through the labeling system that we used. It was just a standard label IMG system. And after all of the images were gathered, we trained it all on Google Colab. Since we didn't have an NVIDIA GPU, the cloud-based Jupyter Notebook was able to train our own custom object detection model. You can see it at the bottom of the screen. It's just really early on in the training iterations, only under 30 out of 2,000. So since we were only training one class, we just found it would be better to train on the cloud-based service. Next slide. Yes, here is the general flow code for the project. It's really simple, just one main loop. The camera will send an image over to the Raspberry Pi and it'll process the image it gets. And if it detects any spaghetti higher than a certain threshold, it'll send the code to stop the 3D printer. If there is no spaghetti found, it'll loop back around to the camera and it'll keep going until the process is finished or it detects any sort of spaghetti. It'll send that G code. M25 was mentioned by Jacob. It's pretty much just an asynchronous pause, and it sends the machine over to the back of the 3D printer until a human can fix the problem or start up the process again.
Some of the challenges and the future improvements, the biggest time is response time. So if you look at that image on the slide, that spaghetti is an extremely advanced spaghetti. I mean, the printer had been running for a significant amount of time, continuously printing, just like that. Unfortunately, all of our training sets, like Gabe mentioned, we got off RoboFlow, like 90% of them were images of that, which is way too far in the failure to be extremely useful. It does prevent any damage to the printer, like in my story in the video. You would stop anything from wedging itself into the fan and causing any significant damage. But in terms of saving the print, that's much too advanced. So future improvement would be to create our own data set. We did with a couple images, but capture early on failures. So as soon as they fail, to train the AI on early on failures. The issue with this, and doing it for this project is just the fact that 3D printing is extremely slow. If you saw my printer, it has a mirror for the bed surface. And as we all know now, machine vision in mirrors, the specular reflection is terrible. So you want to get away from that mirror at least a little bit to get accurate results. So you have to wait for the print to build up. It took me about a half hour for every single print. Many of them took over an hour, depending on the X and Y coordinates of it. So an hour to do every print. If I created a database of 100 prints, that's 100 hours of nonstop runtime, which is pretty significant. And then if you notice the choppy image in the one video for that demonstration, that was another big limitation with just the Pi's resources. It couldn't quite handle the video and the frame rate that we were running with. Gabe had mentioned to me that he's used a Jetson Nano or has heard of a Jetson Nano in the past. And I think that that would probably be a really good future improvement as well. But that's all.
Are there any questions or feedback you'd like to provide?
Thank you, Group 9. Good job. All right. So we're gonna open up for questions here. One thing I can say, can you actually use your printer to print spaghetti, and it will actually let it print spaghetti?
No, I think it'll get caught. We haven't tested it yet, but there are a few prints that do similar stuff. Like there's one that I've seen online that's a lion's mane, and when they print the lion mane, it looks exactly like spaghetti. And I do want to try to test something like that to see if it will stop my printer or if I can continue going.
So let's open up for questions from everyone.
All right, so Larry, again, now I have the video. Very nice project. I really like it. It's impressive, and actually, like you said, I don't have much knowledge about 3D printing other than a little bit of studying here and there, but I think this is a very important type of diagnostics that will provide efficiency, especially when lots of the industry are looking to produce large parts using the 3D printing technology. So it's very important. Did you explore the opportunity of creating this type of, let's say, hardware and software integrations into various brands of 3D printer? Did you look at different, so to create more like a plug and play type of either Wi-Fi communication or Bluetooth communication?
Yeah, so the final result ended up being Wi-Fi for the most part. It does try to detect if there's a UART connection. And if there is a UART connection, it'll send it over UART USB. But it's actually, like you said, more beneficial to use the Wi-Fi. And the AI is another advantage there because I can move that camera anywhere I want with the AI. Whereas when we were doing the rule-based method, it was dependent on calibration. So when we had to calibrate, and if you bumped the camera at all, it was extremely unuser friendly. So the AI was really nice, and it is more of a plug and play.
And the second question would be, like you saying, the detection process, it's coming sometime fairly late. You have to have a pretty large amount of residual printing. If you will be combining multiple cameras, do you think they will be able to detect that much earlier?
Yeah, so one thing we talked about was incorporating both the rule-based method and the AI, because the advantage of the rule-based method is that bounding box. If I did put that up top and monitored the head, I get the speed and reliability of rule-based, but then I get the flexibility of the AI off to the side. So one option is something like that. And I'm sure that even one of the test prints we did where the spaghetti started to print on the back side of the printer. So the camera couldn't see that one. So yeah, just a larger field of view, I think, would be also a very basic way to speed up detection.
Very good. Thank you. Very well done. Thank you.
Thank you.
Great. I have a question here. Would the color of the print matter?
No. The AI generalizes just like based on the data set that we have. So we have a bunch of different colors in the data set itself. So it shouldn't impact any of the detection itself now.
Is your camera doing a grayscale conversion before detection, or is using color images?
Yeah, it just uses whatever the camera itself sees.
Okay. Okay. You mentioned that you tried using the exact location where it should be printing with the bounding box, right? And it worked for small objects. So can you combine both in a way that you are detecting spaghetti plus the small box, because it can probably stop the printer much before you have major Italian food in your 3D printer area?
Yeah, I think that's a really good idea, is leveraging both technologies to get both the benefits, right? You get the speed of the rule-based method and then also the flexibility of AI. So it does kind of pull away. It makes it more difficult if I generalized it for every user to do something like that, because every head is different for every different print brand. But it does give me some more benefits, which would be nice.
And perhaps you could use the shape of the object itself, which is supposed to be printing. Like as humans, how would you detect something is not right when it starts messing up, is the shape is starting to mess up, what the shape should be. So yeah, you could have layers of detections there to make it really robust. But that's a very interesting way the spaghetti method is a really interesting way to detect the error, especially if overnight printing and you don't want the printer to go bad. So good job there. Any last questions for the group? All right, so with that, we are going to move on to our last group, and they are going to present webcam heart rate monitor. Take it away, Group 10.
Okay, just want to make sure everybody can hear me before I start. Okay. Hi everyone. So for our project, we decided to go through with a webcam heartbeat detector. The project consists of me, Kata Cato, Devin Holst, and Troy Cunningham, which you guys will be presented to as the project goes on. And then we're going to start off with our demo video.
Everything is moving, pulsing, vibrating. Some things are subtle, some things are more obvious. Motion extraction is the concept of extracting motion from a video image. This can be done very simply by duplicating your image, displacing it in time, and subtracting the image from the original. This then leaves behind only the motion. Photoplethysmography, or PPG, uses this difference method to track the flow of blood through a person, and thus track their heart rate. This is the exact same method used by optical heart rate monitors that can be found in hospitals and smartwatches. For our project, we built this functionality into a webcam. The program works by creating a buffer of images and then uses a Fourier transform to extract the difference in the images. If you look closely, you can see the blood flushing through my face and pulsing through my hand. Then the pulses are calculated into beats per minute. The result looks like this.
Okay, so I wanted to go into first the purpose and why we chose this device. So we chose it for mainly two reasons. Improving heart rate health or overall heart health, and then the convenience and versatility of our device compared to what we currently use right now. So currently, heart rate health obviously is the most important thing for us humans, or one of the key things that we need, in order to, live a long and healthy life. Yet in America, there's actually about 48% of Americans who struggle with heart disease. And currently we use like EKGs or ECGs to detect our heart rate or heart BPM when you go to doctors and whatnot. And as many of you may know, that consists of a lot of wires and tapes placed all over your chest, and you have to go to the doctors just to be able to get this type of information. So we decided that we wanted to make something more convenient and versatile for everybody to use on a day-to-day basis. So this webcam heartbeat detector, it helps with this. You can do it, anyone can do it, you can do it from your home, and you only need one piece of equipment to function this device. So it's implemented entirely through a camera. So the convenience of this project allows you to use any camera, and you can even use your phone camera. When I was actually testing this out, I just hooked my phone up to my laptop and I was able to run it and then just have my phone display the camera as well. So it's very convenient, it's easily accessible, and essentially a high-level overview of the project is we're going to be detecting color changes in our faces to allow us to calculate the BPM. I'm going to pass it over to Troy to kind of go over how it works and a little bit more behind the concept of the project.
Sorry. Okay, so initially I'm going to cover how it conceptually works, then I'm going to go into the key process that make it so effective. So PPG is a non-invasive technology that uses photons to measure vital signs like heart rate and oxygen saturation. It works by shining a light onto the skin and analyzing how this light interacts with blood vessels underneath. If we look at the image, we have a optoelectronic component. In our case, we're using a webcam that emits light onto the skin, and the photodetector interprets that light that is reflected back after interacting with this tissue. This works because blood in the arteries absorbs more light compared to other tissues. As the heart pumps, blood vessels expand and contract, changing the amount of reflected light. The photodetector captures these changes and converts them into an electrical signal. And of course, this electrical signal is going to take a waveform which oscillates with the heartbeat, with the peaks representing the systolic pressure when the arteries are the largest, and troughs representing the diastolic pressure when arteries are the smallest. From this data, heart rate variations, From this data, heart rate can be calculated by frequency of oscillations. Variability between the heart rate can be derived from time variations between the beats, and oxygen saturation can be determined by the percentage of oxygen depleted blood cells due to the color differential between non-oxygenated and oxygenated blood cells. And furthermore, breathing rate and blood pressure can be estimated by using far more advanced algorithms that we didn't really cover. So next slide, please. So the key process behind the PPG consists of 3 essential tools: Gaussian pyramids, Fourier transformations, and bandpass filters. The first step utilizes Gaussian pyramids to smooth the image and create a series of progressively smaller versions of it. The process helps reduce noise while preserving important details. By focusing on features at different scales, we can highlight slight changes in light reflected off the skin, which correspond to blood flow. Imagine that zooming out slightly at each step to get a clear, noise-free picture of changing light patterns. The second step utilizes Fourier transformations. This mathematical technique converts data from the time domain to the frequency domain. In this domain, we can break down the changes into individual frequencies. For example, the heartbeat frequency will appear as a distinct signal among other variations caused by motion or ambient light. By isolating this frequency range, which is our heart rate range, we can identify the heartbeat patterns. Think of this step as like breaking a song into its individual notes, so we can identify which note represents a heartbeat. For the final step, PPG utilizes a bandpass filter to refine the signal further. It acts like a strainer because it only keeps what we want, aka the frequencies we care about, and removes the unwanted signals that can be caused by like motion or noise outside the heartbeat range. In essence, the bandpass filter ensures we focus solely on the heartbeat data, making the signal more accurate and reliable. So in summary, the Gaussian pyramids help smooth and focus on important features, the PPG signal reducing noise. The Fourier transformation analyzes the signals, frequencies, and isolates changes corresponding to the heartbeat. And bandpass filters further refines the data, keeping only the heartbeat frequencies. By combining these advanced techniques, PPG systems can accurately measure your heart rate and other important vital signs. And I'll go ahead and pass it off to Devin now.
All right, so finally, we're going to talk about how it actually works and how we can actually implement everything. So this leads us to the heart rate calculation. This tracks how often the skin tone changes, and then it can determine the heart rate from that measured in beats per minute. As you can see from this picture, the green box is the area of detection, and you can also see the BPM written just above the green box. All right, and here is the full flow diagram for our software. I'll go through this quickly. I don't want to get too much into the nitty-gritty, but so first off, we start by initializing the camera and setting the image resolution. Then we initialize the Gaussian pyramid and also set up any constants and variables that we have, as well as setting up the bandpass filter. Now we can get into the main loop. So first, we capture a frame from the camera, and then we get the value from the sliders, which the values that we have set on the sliders are just the amplification of the face, as well as the size of the buffer. The reason we chose this is because depending on your lighting conditions, you may need to amplify the image more or less, but also the more you amplify the image, the more noise there is, and the noise can play with the readout from the Fourier transform in the image as well. So it can kind of play with the accuracy a bit, but that's why we left it adjustable. So then it's once you notice in the image, there's not a lot of noise, then you will have accurate results. Then once we have that, we also lower the image down, crop it in to only detect within that green bounding box. And then we grab a pulse from the image. This is done by using the Fourier transform and going through that image buffer that we'll be creating, and seeing the change in the images from previous images captured. From that, we can calculate the BPM. And then we also amplify the image after that, and then add that amplified image to the buffer. We did this just kind of as like a separate check because I was having some errors before. I was trying to amplify it before adding it to the buffer and before calculating the image. It seemed to have, I'm not quite sure on the, I would have to look more into that, but yeah, we noticed the best when added to the buffer after doing so. Once that's done, we rebuild the frame where we have the original feed from the camera, add in the amplified image, and then we can detect to see if the buffer is full. So if the buffer is not full yet, it displays still calculating. Once the buffer is full of images, then we are able to display the BPM. So finally, just want to mention there are a few downsides to this project I mentioned just earlier. Downsides being it does require good, decent lighting and also low noise coming from the camera. But with our Gaussian pyramid, we were able to get the noise reduction to be used in just standard ambient lighting environments. While there are other solutions for heart detection and heart rate detection for users such as Apple Watches and Oura Rings, our solution is completely non-contact, which is great for users who don't want to wear any accessories. It's also great for more sensitive users or patients like the elderly or infants who don't want to have any wires or any devices strapped to them. So, and here are our references. Any questions?
Can I ask a question?
Yeah.
Yeah.
Can you
Yes.
unshare the screen also?
I think I will. In fact, I have two questions. The first question is that did you verify the results by using, let's say, the common use devices which measuring the heart beat rates? And the second question, I'm not sure how it will work. Like, let's say, for people comes from Africa with a black skin, or let's say from the Middle East. You understand me? Away from the white skin, how it will work for such races? Thank you.
Yeah. So as far as verifying, yes, we did verify it. I used it I borrowed an Apple Watch, used it then. I believe Troy did the same. So we were able to verify the calculations. They were off, I think, by like plus or minus 1 or 2 BPM from other devices out there. And as far as like different skin tones, I have not been able to do a ton of testing. As I was thinking about this, I know it will definitely work better on people with lighter skin. But further testing would be needed for that. I don't necessarily know off the top of my head. I wasn't able to test that.
So these were great questions. Yeah. I think, yeah, the variation in how we look and how we our skin tones, you have to do an extensive amount of testing to see to which it works well and works best. But I can say that if you showed that it does work, so now in Zoom meetings we can detect how excited our participants are when in the meeting. Everybody's heart rate will be displayed with their name.
I was just curious, is this a similar technology to that little clip that goes on your finger when they detect oxygen rates in your blood? Is that using a similar technology with this?
It is, yeah, it's actually very similar technology. The way that one works is they just shine essentially like a red LED through your finger and pick it up from the other side. But yes, it is the same, like mathematically, it's about the same process, yep.
So that technology is works regardless of skin tone. So is there something in there that could be beneficial in this application when testing it for different skin tones?
Yeah, I mean, I think again, I would have to test it myself. I don't know off the top of my head, but I do think the same thing would be either shining different lighting or lighting conditions could definitely help in picking up the different skin tones. But again, the part of the reason we did this project was to not have to be hooked up to any extra lighting or things like that. So again, I can't say for sure off the top of my head. It may still work with people with darker skin, but I don't know off the top of my head.
But there was a good point, Deborah. So those devices use infrared and red and infrared LEDs. And now your application doesn't use any kind of infrared, right? It's just using subtracting the images to see what changes are happening, correct?
Yep. Nope. Yeah. It's just standard ambient lighting and just a standard color image from a webcam.
Okay. Can you explain again how or why did you use the Gaussian pyramid in that application?
Yeah. So a couple of reasons were just to reduce the noise. That was the first one, and also just reduce the amount of pixels we had to process. So.
Okay. Yeah. More questions for the group?
Yes, I do have a question. It is about, did you have any opportunity to do a testing for one subject, but he will be in a different stage? So let's say it will be normal, peaceful, and happy. Then he's gonna be hyperactive, coming from, I don't know, from a gym or something, or will be like in a sleepy mode. So to see the data flow and the comparison between, so in that way you can bring much more information to the analytics, pretty much.
Yeah. Go ahead.
No, we didn't. We kind of had the testing towards the end of the school, so we didn't have a lot of time when we got to it. So all we were able to do is pretty much test on ourselves. And our group.
I guess I did want to add something. I actually did it 2 or 3 times. One of the times I actually did it late at night when I got home from the gym. It seemed to work. I also used it on my phone, and I connected my phone via my laptop, and that worked as well. And for the skin tone question that was asked earlier, I believe my skin tone is quite different than Devin's, and we both got pretty reliable, accurate results when we compared it to our watch. So in the case of our skin tones, me being Middle Eastern, it did work, and it did work after I came home from the gym when my face was slightly different in color than it is on a normal, just sitting day-to-day basis.
Yeah. So I think the whole thing depends on if there is a change which can be detected, because you're working on the difference between when the pulse when you have the heartbeat and when you don't, in between, what is the slight change in the face, and you're subtracting to find a rhythm which will result in calculation of the heartbeat. So yeah, it's a neat project, and then showing that just a webcam is able to do that, that is phenomenal. Like, it shows you the power of what we are learning here in machine vision, that how many useful applications we can derive from a simple image and processing of the image itself. Now, one more question about, did you use any machine learning for the face detection, where the face is, or was it a manually placed box that it's going to detect in this region of interest?
We did not use any machine learning. I did think about using machine learning just to crop in on the box and find the bounding boxes of the face. But we also wanted to be able to use it like it'll also work on your hand. So I wanted to make sure like it, can show that it'll work on multiple parts of the body, not just the face.
So do you think that you could extend this application where there are multiple people in the image and you detect faces and you're individually monitoring them, and you will have heart rate of each one of them separately, because you're processing their face and subtracting it individually. Would that work?
Yeah, it definitely would work. Yeah, I don't see why not. I mean, you just have to segment out each individual person and then calculate the heart rate individual for each segment of the image. But yeah, I do think it would work.
Okay, so that means that you could show with your name your heart rate at the actual heart.
Yeah, if you trained an AI on your face specifically, you could do that. Yeah.
Okay. Any last questions for this group? All right, good job, group 10.
Thank you.
Very neat project. Okay, so now we have seen all 10 presentations and really good, very creative stuff, I have to say. And I'm very impressed with, your involvement in trying to come up with some neat way to apply what you have learned in the class and some real practical applications. So before closing, if any of our guests wants to say a few words on the projects you saw and the creativity of the students, please go ahead.
Just congratulations to everyone for completing everything. Really impressive. Coming from a non-technical background, it's really impressive to see all the applications and all the things that you're doing.
Yeah,
Thank you,
same
Deborah.
as Deborah. Very non-technical here and great job explaining it so I could understand, and really well done, everyone.
Thank you, Laura.
Yes, sir. And thank you for inviting me. It was really a pleasure. I was have to bounce between some of the meetings, some of the phone calls, but I was very happy to participate. Thanks again, and very impressive with the work and the dedications. And the projects you develop pretty much have a very, very large scalability, and they can be used for many, many other aspects, in the real life. So thank you very much. Very well job done. Thank you.
Thank you, Larry. All right, so with that, congratulations, everyone. You fulfilled your final project requirements, and now there's only one more final exam to go, and then you're home free. And prepare well, and we look forward to seeing you actually use machine vision in your careers. And I want to see, some real cool things coming out of what you learned in the class. Thank you, everyone. Have a great day, everybody.
Thank you.
Thank you, Professor.
Thank you.